false statement, so that point is not a solution. It does not satisfy the equation when you plug in that xy. It's not an ordered pair that satisfies. And you can also see -2, -8 visually. It is right there, and so it is off the graph. So this is a solution, and this is off the graph. It does not satisfy, so it is not a solution. All right, okay with that? Okay. So there'll be a couple of those to practice on homework. And some of the ones you see on the show up in my math lab are a little more, this is some pretty basic numbers to show the procedure. You know, a lot of times you're going to on the math lab, you'll see like more fractions and negative numbers and such. Okay? So use the calculator to assist. Make sure you plug things in parentheses. Remember, anytime you use a fraction in the calculator, it should be in parentheses. Okay? Otherwise, the calculator gets the order of operations wrong. Okay? So if you write it down visually first, whatever the number is, in parentheses, and then you can just enter the entire thing in my math lab. You can enter just like you're testing a solution to a single variable. You know, plug in those numbers, but don't try and store the number, because then you have to store 2 different letters, and that makes it more complex than it has to. For example, the calculator, you just enter -6, and then you go to the math test to get the equal sign, and then do 2 parenthesis 1 parenthesis -8, and then when you push enter, it's going to tell you 1 for true and 0 for false. Okay. The only difference between this and checking the single variable is I said, with the single variable, just store your solution, so all you have to put in is an x. Okay. You don't have to store a solution. You can just put them in yourself. You can choose an x and a y on your calculator, but it makes it more messy than it needs to be. It's easier to handle it a little, but when you're dealing with fractions, that calculator can be a good backup as well. Just be careful about negatives also, and where you're entering it in the correct place, x or y. Okay. So here's the solution. All right, good. Okay. All right, so far? Okay. So let's look at the forms of the equation and how they talk to us and the real key points. Let's take that y equals 2x minus 8. And I'm going to just rewrite the chart here real quick, but just in a much cleaner form. So -1, 0, 2, 4, and -10, -8, -4, and 0. Okay. So that was the table of values, what's called table of values for this equation. And you can graph anything of any family by using a table of values, but as I pointed out, it is the most tedious and least efficient way to graph. It's better to figure out how that equation's talking to you, is try to tell you what it looks like, and graph it that way. It's important to understand the table of values because that shows you how things, ordered pairs are generated and whether they are, satisfy the equation or not. That's an important concept, but it's not the most efficient thing to graph. Okay. All right, so here, as Rose already pointed out, these are 2 out of all the infinite possibilities, ordered pairs, infinite ordered pairs. Those 2 in particular are special. If you ever see an ordered pair for a line, now line doesn't curve or bend, graphs that curve or bend can have more than one x or y intercept. Okay? How many x-intercepts will a line have?
1.
And y-intercepts? 1 of each, because it doesn't curve or bend. Okay? So with a line, when you see a point with x equals 0, that is the only point out of all of those infinite points that will have x equals 0. Okay? No ambiguity there. Oh, here's the point 0, -8. That means this is the y-intercept, right. If x is 0, y-intercept. And here's a point where y equals 0, so this is the x-intercept, period. If you know it's linear, and you see a point out of the infinite points with a 0 in it, you'll only see 2 points with a 0. One that has an x equals 0 and one that has a y equals 0. That's the only ones that will have zeros in them. Those are 2 special points. That is the definition, as I sort of noted earlier. That is the definition. When x equals 0, you have the y-intercept, by definition. Okay? And when y equals 0, you have, by definition, the x-intercept. Now, if you see this point with an x0 or y0, you know you have the intercept. If you don't know the intercepts, then all you have to do to find them is plug in x equals 0, and you'll have the y-intercept. Or plug in y equals 0, and you'll have the x-intercept. Okay, so you can identify the points visually, or you can find them just by understanding the definition. Plug this in, solve for y. Plug this in, solve for x. Okay. Now, noting these points right here, this y-intercept specifically is the point 0, -8, and this one, because that number is not just the number that's the intercept, but it's the entire point. 4, 0 is the x-intercept. Now, visually, look back at the original equation, the original function, and do you see anything that sparks, anything that stands out, comparing the intercepts and the equation?
-8 with the 0 -8, so that shows you your y-intercept.
Right.
Your 4 and 0, which is...
Now, do you see a 4 in here?
Well, no, but you just plug in the...
Right. Yeah, but just visually, just sparking, just what you see, hopefully that's what stands out right there. Now think back to our absolute value when I graphed the absolute value. And remember how doing like a plus 2 raised it up to on the y-axis? And a -3 dropped it down by 3 on the y-axis? Y-intercept. Where do you think this line falls on the y-axis? At. So that line has been dropped down the y-axis to -8. Okay? This is the function, y equals 2x, and this whole function has been dropped by 8 on the y-axis. Okay? So if you had plus something, this whole line would be pushed up above the origin by that many. Okay? That plus or minus at the end raises or drops your whole function. Okay? So right there, and now this is specifically when it's in this pretty form. This isn't what's called function notation when it's solved for y. Okay? And so this is only the case right now when you are in this form. We're going to look at another pretty form. This is one pretty form, and there's another pretty form. And if it's not in one of the two pretty forms, you should put it in one of the two pretty forms, because that's when the equation talks to you. Okay? And you put it in the pretty forms by using your properties of equality to move things around till they look like they're in the proper pretty form, which in this case is solve for y and then equal to something x plus or minus a number. Okay. So, where I see right there is the y-intercept when it's in this solve for y pretty form. That constant is your y-intercept. Okay. Let me make sure I'm not skipping that. All right. So, the other thing that we can really tell, the other way the line talks to us, specifically in this form, it tells us without any math, without having to do any math, it tells us the y-intercept. Boom, right there. This is where this line crosses the y-axis. Okay? No math involved. There it is. Okay? The other way this line talks to us, and if we want the x-intercept, all we have to do is plug in y equals 0 and solve for x. Okay? And we just add 8 to both sides and divide both sides by 2. We get the 4, like expected. The other way this line talks to us, this equation talks to us, and the other characteristic that is so important to know about a line that we need to know to graph it, to visualize it and graph it, is its slope. Okay. Now, next week, as I said, we're going to do more of 8.4 and go a little bit more in depth into slope and what it means in sort of like real-world applications, you know, what the slope really means. But just to touch on now and be able to find it and be able to graph, slope is, specifically, the basic definition of it, it is the steepness of a line. Okay. Now, the more algebraic definition that we will explore more next week is that slope is also known as rate of change. Rate means just how fast. Okay? So how fast things are changing. Now, a line doesn't bend or curve, so does its rate ever change?
Yeah.
I mean, does the steepness of a line ever change?
No.
One particular line?
Not in the same line, no.
Yeah. I mean, if you look at here.
It'll have the same slope.
Right. Yeah, so we've got these particular points, and we've also got infinite other points. And if you know 2 points on a line, you can find the slope because you find how steep it is between those 2 points. So if I use these 2 points, and you use these 2 points, and someone else uses these 2 points, are we all going to get the same answer? Yeah, because the steepness of a line doesn't change. Visualize it, think of it as like you're walking up a hill or a mountain. Okay? Usually when you go on a real world hike, oh, it's steep for a while, and then it's a little flattens out a bit, and then it gets really steep, and then it starts to go down. Some graphs are like that, but not a line. The steepness is always the same. That means the slope is always the same, and that means the rate of change is constant. Okay? Constant, as it's constantly the same, it doesn't change. Okay? Other graphs of other families do not have constant rates of change. They don't have constant slopes, and every point will have a different slope. But with a line, the slope is the same everywhere. Okay? If it wasn't, it wouldn't be a line, because that meant it bent or curved. Okay? So it doesn't matter what points we use to find slope. We've got that constant rate of change. Back to, like I said, we'll look a little bit more at that sort of real-world understanding of rate of change and how that works in like real-world applications with slope, because that tells us so much information about things that have linear relationships, are real-world situations that change at a constant rate. So we can predict things in the future. We can map things from the past if we know that constant rate of change, that we have a linear relationship. Okay, so other ways to think about slope as far as calculating slope, and we're just going to do it visually today in graphing, is rise over run is the classic one. A stair step has rise, how high is the step, and run, which is how deep is the step. And depending on the length of the rise and the length of the run, steps can be very steep or very shallow. And that also, while the line is a ramp, not staircase, we still count it like stairs to find how high it goes up, and then what's the run, the rise over run. And the rise, the vertical change, is always first on top and the horizontal change on the bottom. We can write that algebraically like this. Delta y over delta x. Delta, that's just a Greek letter delta, and mathematically it means change. And change means subtraction, difference. Okay? So the difference between two y values, you pick 2 points, and the difference between two y values goes on top, and the difference between the x values of those 2 points on the bottom just means subtract. Okay? Written out, what that means is vertical change, always on top, over a horizontal change. And when you're counting this out and graphing it, you literally go up, which is positive, or down, which is negative, first. So you pick 2 points, and to move to that second point, you're going to move up or down first. And then to get over to that second point, you're either going to move right, which would make it a positive number of units, or left, which makes it a negative number of units.
But you can also just get the number from the formula, right? Like just 2 over.
Yes, exactly. And that's the kind of connections we want to make. So let's look at our graph of the line we graphed. So good? And let's pick 2 points. Okay. Let's pick this point and this point right here. And you can remember, you can pick any 2 points, but to get from this point to this point, how far up do I have to go? How many units?
4.
Right. Now remember, distance is always positive, so I'm not worried about like whether these are negative numbers or whether I cross an axis. I count 1, 2, 3, 4 units. And since I'm going up, is it positive 4 or negative 4? Positive. Right. So that's 4 units up, and then to hit this second point, I went how far in what direction? 2. So that's 2 positive or negative? Positive, yeah. 4 up, positive 4, 2 to the right, positive 2. Also, visually, I see this is an upward line, which so I'm expecting positive slope. Okay? The more you recognize that, the more when you look at a line and go, oh, I know by looking at the slope of that line that it's going to be an upward steep line or a downward shallow line. And then when you draw the line, you can I do this all the time. I draw my slope in the wrong direction, but because I already visualize it before I start, I catch my careless mistake right away. So it's a habit to be in, and we'll see that when you look at the equation, how you can predict what it should look like. So here our slope, and we use the letter M for slope. Our slope is equal to rise of positive 4 over a run of positive 2. Now let's count from this one to this one. So to get from this one to this one, am I going to go up or down? How many units? 6. Positive 6 or negative 6?
Negative.
Right. Because it's 6 down. And now to get to that second point, how many units in which direction? To the? So positive 3 or negative 3?
Negative.
Right. So our rise was negative 6, and our run is negative 3. Well, I told you earlier that on a line, slope is always the same. Those look different. But they're not actually. They reduce to?
2 over.
Right. So it reduces to 2. Or 2 over 1. 2 is what you'd put in the equation if you were writing the equation of this line. 2 over 1 is what you'd use for counting purposes because slope is a ratio. You need 2 numbers for slope. If your slope is a whole number, just put it over 1. Okay? And then this would be, you could always hear from this point to this point, 2 up, 1 to the right. Boom, slope of 2. 2 up, 1 to the right. And remember, 2 negatives, if it's a positive slope, that means you've got 2 positives or 2 negatives. A downward line, negative slope, will have 1 positive, 1 negative. It doesn't matter whether the negative is on top and the positive on the bottom or vice versa. Okay.
So I have a question. Like just by looking at the equation, shouldn't we already know that the slope is 2?
Yes.
Rather than doing all of that?
Exactly. If you were given a line and you didn't know that, you can find the slope by counting off. Okay? And then I want us to make that connection, given that you know this is the equation of the line, what do you see that sparks? Right. Yeah, so you don't have to do both. It just means you can go in either direction. That's the relationship. All right?
Earlier you had like on the y, where you were like if it's negative 2, you go to the right. So you ignore that for the slope.
Say again, sir?
Like earlier you were like if it's negative 2, you go to the right.
Like counting off the slope?
Yeah.
Negative 2 would be 2 to the left if it's on the bottom, or 2 down if it's on the top. So like, you mean right here?
No, earlier.
That's only when you like slide it over like
Yeah.
Like with the sliding it. Yeah, that's for graphing a function. Yeah. Put that out of your mind here because that's just when the x is affected with something added or subtracted to it. Remember how like with the absolute value when we put a coefficient in front of it, it shrunk it or it expanded it? That's what slope does for a line. But instead of like shrinking it or expanding it, like with absolute value, the coefficient in front of x, 2x or half x, made the v either taller or fatter. The slope of a line has the same effect, but because it's different than other function, it's different looking. That's why I said absolute value is a little easier to sort of see that, but the slope of a line just changes how steep it is. Okay. Yeah. So what you're multiplying times the x changes either its contraction or expansion, or in the case of a line, it changes its steepness. Remember, absolute value is just 2 lines. So when you're affecting the steepness of both those lines, that's going to make it either skinnier or fatter. If it's just a single line for a linear equation, then that coefficient of x is like changing half of the v. Okay. You can think of it kind of that way too. Now anything added or subtracted is what shifts it up, down, left, or right. Now with a line, we don't worry about shifting left or right. We just worry about shifting up or down. That -8 meant shift 8 down. And the slope of 2. So what sparks here is that our slope in this case is 2. That's our slope, or our steepness. And we can see that without doing the math. If we don't know the equation, we can count it off. If I just gave you this line without the equation, you say, oh, well, let's see. All I need is the y-intercept is -8, and I can count off the slope and find it's 2, and so the equation of this line is y equals 2x minus 8. Boom, you can write the equation of the line without knowing it. But if you already see that, now you can graph it. Put a point at -8 on the y-axis, and then count off a slope of 2 over 1. That gives you your second point. Connect the dots. Right. All right, so here's the form. Here is the, aside from the y equals 2x minus 8, here's the form we've been working with in algebraic terms. Y equals mx plus b. Yes. Good. It's all clicking, right? Okay, good. Like I said, I hope today is like, not boring, but like, oh yeah, I remember this, you know, or hopefully it's clicking too if it was it was a while ago, or let's see. All right, so this tells you when your equation is in this form, this is one of the two pretty forms of a linear equation. It's linear if you have a degree 1. It's linear if the exponent of x is 1 and you don't have anything else, a nice clean x and a clean y. That makes it linear. But that doesn't mean it has to be in a pretty form. It just has to have a clean x and a clean y somewhere in there. Okay? But if it's in one of these two pretty forms, then it talks to you, it tells you everything you need to know, both intercepts and a slope, and you can graph it. So this pretty form is named for exactly what it tells you, which is slope-intercept form. Slope-intercept form of a linear equation. Because different families have different forms. Okay? So slope-intercept form of a linear equation. And without doing any math whatsoever, this gives you enough to graph it. First, you graph your y-intercept. Your y-intercept is not b. So if I ask you what's the y-intercept, don't just tell me the number that's b. The y-intercept is a point. Okay? So your y-intercept is the ordered pair 0, comma b. Okay? It is an ordered pair. That is the ordered pair that happens when x equals 0. Now, if x equals 0, what happens to the mx?
Over 1.
Well, when x is 0, so you'd have m times 0. So when x is 0, what happens to mx? Yeah, it would be equal to 0, and which means it goes away, right? So if x is 0, m times 0, whatever m is, times 0, mx disappears. I can cover it up. Huh? My point is when that's why this form is so nice for showing your y-intercept. That's why b is your y-intercept, because if x is 0, the definition of a y-intercept, that means that your mx goes away and y equals b. When x equals 0, y equals b.
So it'd just be a horizontal.
Except that this is if it has an x and a y, it's a diagonal line. I am only plugging in a 0 for either of them to find the intercepts of that diagonal line. But yes, if you start off with an equation that only has an x or only a y, you have a horizontal or vertical. We're going to go into that more on Tuesday as well, too. Yes, that'll come back up. Right now, this is if it's an x and a y, clean x and y, it's not only a linear equation, it's a line, but it's a diagonal line. And if you plug in x equals 0, then y equals, in this pretty form, y equals that b. So you can just go automatically, 0b, because x was 0 and that b is your y-intercept. Okay? And without any math, you can find the slope, because all it is the coefficient of x. Okay? Now, I'm emphasizing coefficient of x, because one common mistake I see is that people put the slope, like of the one we've been working with, as 2x. If you put the slope as 2x, that's very wrong, because x is a variable, and that would mean that the slope of a line changed. Because if it has a variable in it, you can plug in something for x and the slope would change. Does the slope of a line change? The slope of a line is constant. Therefore, the slope is a constant. It is just a number. It is just the number. Just the coefficient, not the x. Okay. Now, the little part you do have to do math would be to find the x-intercept. And that's in order either because I asked you what's the x-intercept, or because you want to find it just to make sure to check your work. When you plot that point, you count out the slope, you draw your line, then find the x-intercept to check your work. So sometimes the x-intercept is a fraction and all, but you can at least visually see, yeah, that's fallen in about the right place. So it's a good check on your work. So to find the third thing then to find is the x-intercept. And the x-intercept, all you do, the very definition of x-intercept is plug in y equals 0. Okay? And then you solve for x. Okay? And so your x-intercept is whatever that x is, comma, y equals 0. 2 points and a slope. You only need 2 points or a point and a slope to graph a line. The third piece of information helps you check your work, or if you're asked for it specifically. Okay. Hopefully I'm going to have time to show standard forms too, as I did in my other class. But first, let's make sure we're comfortable with the graphing. Okay? There's not a lot of graphing on this first homework. Like I said, I'm going to give some more hand graphing practice for the weekend. before we do it more in class on Tuesday. But let's just make sure this information, good, on paper, let's put it into practice. So on here, first, there's a couple comparisons I want to make. So on this first graph right here, this one on the right here on the top, graph 3 lines on the same graph and see what happens. We've got y equals x. Now, just like I showed on the Desmos with the absolute value, y equals absolute value of x, and I call that the parent or the mother function. Right? This is the parent of the linear family, just like y equals absolute value of x is the parent of the absolute value function, family. Okay? So this is your basic, middle-of-the-road, no frills, mother of the linear functions. Everything else has a different, this is a slope of 1, and it goes through, it doesn't have any shift up or down. Okay? And so you start putting other coefficients and other shifts, and you start getting other lines in the family, but this is the mother. Okay? So, and then on the same graph, y equals x plus 3, and y equals x minus 5. Now, your first job in graphing these, if you see, hey, these are solved for y, slope-intercept form, let me plot my y-intercept and then count off my slope. What is the slope of these lines? 1. Remember, it's the number. Yeah, it's the coefficient of x. Now, we don't have to write the 1, but if you don't see it, there is a 1. Okay? So, is that a positive or negative slope?
Positive.
It's going to be upward line. Is it going to be steep or shallow?
It's just going to be the normal one.
Yeah, it's going to be medium. One slope is the medium, right through the middle slope. Any slope, absolute value of slope that's bigger than 1, it gets steeper, the bigger the steeper. And anything that's a fractional slope, like a proper fraction slope, is a shallower line. Okay? So these all have the same slope, so how are these going to interact on a graph together? If they have the same steepness, they're what?
They're going to be
parallel, right. So they'll only be on top of each other if they're the same line, but parallel means they'll never cross. Right. And this one doesn't have a B. Right. There is a B, it's just 0. Right? So I said there's always one x-intercept and one y-intercept. What's the y-intercept of this line?
0.
Yeah. 0, comma B, and B is 0, so it's 0, comma 0. It is the origin. So what's the x-intercept of this line?
0.
Yeah. If it goes through the origin, it still has 2 intercepts, but it's the same one at the same time. It goes through both axes at the same point. The origin is that one place that happens. Okay? So if you've got no constant, you go through the origin. And then with the slope. And the slope is 1, but for counting purposes, 1 over 1. Or negative 1 over negative 1. Okay? It's going to fall same way on the line. 2 positives or 2 negatives. Okay? So I'll use different colors. I don't think it shows up totally well here, but so we got 0, 3. So this is the kind of speed and confidence I want you to have with these lines. Oh, slope-intercept form, plot my y-intercept, count off my slope. Now with a tiny slope like 1 over 1, you want to give it a couple, 1, up 1 over 1, or down 1, 1 to the left. Okay, you can go in both directions. Check, okay, positive slope, upward medium line, check before you connect the dots. Okay. If you already visualize what you're expecting, an upward medium line, then you can catch yourself in case you go in the wrong direction before you